The topic of this presentation is water use rates, or also known as evapotranspiration. 99.9% of the water used by an irrigated turf is drawn through the roots and transpires through the leaves. Only a small fraction, about 0.1%, is used for plants to produce plant tissue. Evapotranspiration is comprised of plant transpiration and evaporation. Transpiration refers to the water lost through the leaves, and evaporation occurs when water changes to a vapor on either the soil or plant surface. Given a complete turf cover for most of the growing season, the majority of seasonal evapotranspiration is from transpiration. Transpiration losses are usually high and linked to plant growth and productivity. This is because the pathway for transpiration in plants is the same one that allows for plant intake of carbon dioxide. Both exchange processes occur through the leaf pores called stomata. Stomatas are fully open when plants receive enough water through the soil and when both transpiration and photosynthesis are occurring at maximum rates. If soil water becomes limiting, stomata begin to close, causing a decrease in transpiration and photosynthesis. Water use rates, also referred to as evapotranspiration or ET, are expressed in terms of inches or millimeters per day normally, but are given too on a longer basis, like a week or a month or a year. The primary factors affecting evapotranspiration, or ET, are sunlight, air temperature, relative humidity, and wind speed. These weather components determine the amount of energy present to evaporate water and drive transpiration. As sunlight, temperature, and wind increase and the relative humidity decreases, ET increases as long as adequate soil moisture is present. The data collected from these measurements are plugged into the Penman-Monteith equation to estimate the reference evapotranspiration. This is an overview of the equation. Notice again that the data collected are the major components in the equation. For your information, the Penman equation was developed in 1948 to predict evapotranspiration. The term reference evapotranspiration refers to the ET equation calibrated to estimate the water use of a well-watered alfalfa or grass field under a set of local weather conditions. In Colorado, for example, the State Agricultural Meteorology Service uses alfalfa as the reference crop. In Arizona, a cool season turfgrass is used, most likely tall fescue. In Arizona and other states that use a turf, usually it's maintained at a height of about 4.7 inches or 12 centimeters. For calculating the water use rate of turf grasses, the assumption is made that sufficient soil water is available and will not be a limiting factor for transpiration. Given there are thousands of plants, we can't have a reference cover for each one from a practical standpoint. And in the case of turf grasses, we rarely grow a turf that is equivalent to the reference surface. Adjustments need to be made. An adjustment is necessary to convert the reference ET values to estimates of the actual turf ET. The adjustment process is quite easy and consists of multiplying the reference ET by an adjustment factor known as the crop coefficient. A variety of factors impact the KC or crop coefficient value for turf. The most important are type of turf, whether it's cool or warm season, turf quality, stage of turf development, and turf height. Stage of turf development refers to mainly the time of season. For example, water use by Bermuda grass is lower during spring and fall during the transition period than during mid-season. Let's look at a little closer at these factors that influence the KC or crop coefficient. Environments that are hot and dry will have the highest ET rates. This table provides the potential evapotranspiration rates for various climatic situations. Altitude can play a role in water loss. Higher altitudes tend to have higher evapotranspiration rates due to the lower atmospheric pressure. The length of the growing season influences water use rates. The longer the growing season, the higher the annual water use rate for the turf. The highest water use occurs when the turf is actively growing, usually late spring through early to midsummer, and is the lowest in the winter. Winter overseeding in certain regions artificially increases the growing season. For example, where Bermuda grass may normally go dormant, as shown here on this golf course fairway in South Carolina, by overseeding, the seasonal water use increases because of the presence of the growing of the cool season turfgrass. Water use rates vary among turfgrass species. This photograph is of a creeping bentgrass green surrounded by Bermuda grass. When directly comparing water use rates between cool season and warm season turfgrasses, cool season turfgrasses have a higher water use rate. Cultural practices like mowing impact water use rates. The higher the height of cut, the higher the water use rate. Generally, turfgrasses that have more vertical leaf orientations and higher leaf extension rates have higher water use rates than grasses with horizontal growth habits and limited leaf extension rates. Besides height, mowing frequency can affect water use rate. In a study done by Sherman and Beard, they demonstrated that increasing the mowing of creeping bentgrass from 1 to 12 times in a 14-day period increased water use rate by 15%. Thus, more frequent mowing, especially on greens, is likely to increase water use rates. Turf subjected to increased traffic and wear have higher water use rates. Where the turf is worn from golfers entering and exiting this green is higher than where wear is minimal. Biotic stresses like diseases, in this case rust, can increase water use rates. Rust pustules rupture the leaf epidermis, increasing water loss. So let's go back to these Kc values and actually look at an evapotranspiration calculation. If we retrieve a reference ET of 0.24 inches from a weather station, and we use a Croc coefficient of 0.9, the calculation is 0.9 times 0.24, which equals 0.216 inches. In this case, our turf has used approximately 0.21 inches of water for the day. Why is this important? Where irrigation water use is highly regulated, especially in the western United States, this helps determine how much irrigation water to supply. Croc coefficient values can vary during the season. For example, listed below are Croc coefficients appropriate for use with reference evapotranspiration values generated by the Arizona Meteorological Network. So for this situation, the turf surface was overseeded with ryegrass from October through May. Tifway Bermuda grass served as the turf surface from June through September. Mean seasonal Croc coefficients for your information are listed on the left under winter and summer. So this turf would be maintained at a high quality fairway turf. This graph of the range of Croc coefficient values for cool season turf grasses is based on tall fescue, but are widely used for almost all cool season turf grasses. During the summer, 0.8 to 0.95 Croc coefficient value is appropriate for delivering a quality turf. In this case, using a higher Kc value would be appropriate for a higher quality turf desired, and turfs that may have less heat tolerance. Lower Kcs or Croc coefficient values suffice for a lower quality turf or more heat tolerant type of turfgrass species. The useful range for Croc coefficients for warm season grasses falls between 0.6 to 0.8. Below this range, the turf suffers stress, and above it is likely to be too wet. Deficit irrigation is a term used to describe irrigating with the lower end of the Croc coefficient values to reduce the amount of irrigation water used on turf. Warm season turf grasses are most tolerant to deficit irrigation, while cool season turf grasses, except for maybe tall fescue, are not. For high-quality cool-season turf grasses, watering close to the reference ET produces the quality of turf most expected on athletic fields and golf courses through the summer. Watering at lower crop coefficients can cause stress and lower quality turf. The reference ET we have used to calculate water loss from our turf is for that day. The National Weather Service has a website that predicts the reference ET for the next day or for 7 days out. This is a way to predict how much water will be needed to replenish that turf for up to a week. This is a pretty powerful tool, especially in the western United States under arid or semi-arid climates where high ETs exist. When we go to the website, digital.weather.gov, we will see this screen. Now if I go to the second drop tab from the top left and click on fret, this will give me the ET in inches. The following will be displayed, giving you an idea of reference ET values from around the country. Here in Columbus, it looks like the value is 0.22 inches. You can focus in on an area of the country by clicking on the arrows to the left of the map. Now let's choose a total weekly fret, or a 7-day total, from the same drop box we used previously. We see the upcoming ET rate for the week. Here in Columbus, it looks like about 1 2/10 inches. Again, this is a predicted reference ET and is based on a grass cover mowed at 4.7 inches. This 1 2/10 inch will be needed to be adjusted using a KC value. Being a cool season turf grass, that range could be 0.8 to 0.95. In this case, if we use a 0.9, then our turf evapotranspiration loss is about 1 1/10 inches. Looks like golf courses and athletic fields will need to be putting down supplemental irrigation for the coming week. Monitoring the ET rate is an important tool in applying the proper amount of water to a turf, based on the functionality and quality desired of that turf. As water restrictions become part of the landscape, calculating and using water will be a cornerstone for many golf courses and athletic fields throughout the world, which will be most prevalent in arid, semi-arid, and desert climates.